Good evening, everyone. Today we have a short technical seminar on controls kit inner workings. We had a seminar, a joint seminar, or JetBrains Research seminar with another laboratory some time ago, and there is a recording on our channel. Not on our channel, on the JetBrains Research channel. And I think this one will also be published either on our channel or JetBrains Research channel. And today is a technical seminar, so we are going to dig deep into the details of implementation. I mean, the coroutines, event loop, and integration with the different transport protocols. I will start with a short repeat of the presentation I gave last time, and then I will draw some pictures to easily better understand how does different control system and microservice operation works. And then we will go to the code and see how it is implemented inside the code. Please feel free to ask your questions anytime, both in English or in Russian, and I will translate if we need that. So I'm going to presentation. I'm going to be pretty fast about it because that's the second time I'm showing it. First of all, what is a control system? The control system is some kind of software which allows us to both read values from devices and write values to devices. So we are going to read some kind of state or readings from sensors, and we are going to change properties. For example, turn on or turn off some devices or switch positions or whatever. And all modern systems operate in terms of properties or attributes. For example, in Tango controls, it's called attributes. In other systems, it's called properties, meaning we have some kind of read-only or read-write properties in each of our devices. And then we need to control those devices and switch properties, for example. And it could or could not change some physical state. For example, we have a kind of device server, and we call it device server because it is then connected. Then the control system is connected to this device server externally. And we can read some information from port. It could be USB port or RS-232 or RS-485 or whatever you want. And you can send information there. And also, usually those device servers include some additional things like storage, logging, etc. And the control system, of course, is a much more complicated thing because we need not only to send those things locally, but we also want to read and write those properties remotely. For those of you who do not have experience with the SCADA systems, consider you have a light bulb in your room and you want to just press a button on your mobile phone and turn on the light, turn the light on, or even issue a voice command about it. So everything is working more or less the same way, with the exception that when you are controlling everything from the mobile phone, you have a central point of your system, your mobile phone, which controls everything. And when we are talking about the control system, there is no specific central point. And it is possible for all devices to communicate with other devices. And there are also services like storage service, monitoring service, etc. And most of the systems that are now developed in terms of remote procedure call, peer-to-peer communication. And what I'm going to talk about today is some kind of different system which uses not directly communicates with other devices, but sends and receives events and uses a central event loop to distribute these events. This way, it's much more like modern web services than the classical SCADA systems. Okay, and of course, there is problem not only with this message passing system, but also with developing the device server itself. And it should be easy. So a guy without a lot of programming expertise should be able to set it up and establish all properties. And for small experiments, like, for example, non-accelerator physics, where I work, it is also important to be able to run those devices in a standalone mode without connection to this huge, complicated SCADA system. And modern systems mostly do not allow this possibility. What is important from the implementation point of view is that we are talking about a three-layer system. So consider, again, this example is a mobile phone, and we have three actors here. We have a mobile phone with a button. We have a server, software, which controls the light bulb. And we have an actual electrical relay, which could be turned on or off. So we have a remote state, we have a logical state, and when we have a physical state. When you are thinking in terms of asynchronous systems, and here we're talking about asynchronous systems, you need to be very aware of different states in your system. So you can't just assume that the triggering logical state simultaneously switches the physical state, or that the triggering remote state simultaneously changes the logical state. So there are several different workflows about how events could propagate from remote. Physical state could be changed, and it notifies that the logical state changes, and then it sends events to the remote. There could be some timed updates. Then you trigger self-check. There you actively check that the state is changed or not, and send the event if it is changed. And of course, there is a classical request-response scheme. And of course, when you are working with an asynchronous system, you always need to be aware that each of those requests could produce errors. So a lot of things could go wrong.
Hi, Alex. Thank you for the nice talk. I just wanted to add one thing here is that sometimes you also need to add logic to the fact that this server or the device you're running on might fail. Like someone passes in the building and switches the electricity off, and then you put it back, and then it restarts. And this sort of logic is it somehow in, like, I'm sorry, I'm going to give you this example from Scala, just because it's sort of, but we have sort of, we treat every single service as a separate actor. And then there is a whole API, if you know what I'm talking about, where you sort of design the whole life cycle of the service. So when it starts, when it sort of receives messages, how it responds to messages, if it fails, what does it, how it kills itself and then restarts. So there's a whole, is it somehow embedded into your library?
Yes, there is no fail-safe against failing services, because when you are working with microservices, you usually have some kind of duplication. So when one of the services fails, there is another services to take its role. In case of devices, if device fails, it cannot be duplicated. So in general, SCADA systems do not have out-of-the-box way to control if some kind of service is dead. The only way to understand that the service is dead, where is my mouse pointer? In this scheme is you send a request and then you get the timeout on response.
So you need some sort of heartbeat.
No, yes, usually it is.
So you have a central manager and then you got heartbeats to the devices coming through that manager?
Basically, they're not central, but usually they do additional service called watchdog, which from time to time sends signals to those device servers and check if they are okay. So, but in this architecture, it is a separate service, and I will draw some pictures. I will show you where it is. Okay. The one problem I probably want to talk a lot today is the communication format and the property format, but it's actually one of the most critical problems, because you need not only to write those properties and read those properties, but you also need to transport them by network. And for that, you need some kind of transport protocol. And one of the problems of SCADA systems is that each system has its own, usually undocumented, and in some cases proprietary protocol for encoding those values. And this is a huge problem. They're completely incompatible with each other, so you can't use two different SCADA systems together, and they usually could be used only in the language they are coded. For example, in Dux, you have to use C++ because it's not only an outdated protocol, I mean Sun or in C, but it's also some things are hard-coded in the C++ code, and it's very hard to replicate them in any other language. You need to reverse engineer the whole system for that. And it's a huge problem, but I probably won't talk a lot about it today. So what we are going to use, we're going to use common JSON as a base standard for our encoding, so it simplifies things a lot. And I will get back to that and show you, it's probably a little bit outdated. I will show you how it works in the code later, the actual device server. So we can skip that. One of the problems, and I will show you now, it's in a drawing, it's a synchronous versus asynchronous systems. And most of today's SCADA systems are synchronous, meaning that you always have a request and response. And when you have a request, you are blocking and waiting for the response. And it has a lot of advantages. For example, you do not suffer from dead devices. If you have a timeout and you understand that the one you are calling is dead, and you are sure that your message was delivered. In asynchronous system, usually you do not have good delivery guarantees, and you do not know in which order responses for a request will come back. But on the other hand, the asynchronous systems are much more scalable. So you can just improve the throughput of your event loop and include as many asynchronous systems, asynchronous communication devices as you want. Okay, that's all for the presentation, and you have some questions you can ask them now. Meanwhile, I will switch to drawing mode and draw some examples. I want to talk a little bit more about those asynchronous systems, and for that I will need to draw a little bit. Consider we have one device and another device and device number 3, and we want to communicate. A simple thing is that you make a request and get the response, and then you get a request here, and then you get a response, and that's okay. And we are not talking only about devices, because we have can have a data storage system here which does the same, and for example asks each device in turn, like in cycle, what the state do you have, and please answer me, and I will write it down. And you can have a watchdog system, which
actually, yes, I showed that you are talking about this sort of random messages passing, but still in many use cases you want to have some sort of timeline about how do you say, switch on the devices. For example, you want to first make sure that you started the database and then you started your devices before you collect the data. And if the database is down, then you sort of want to somehow.
But usually there is some kind of mechanism like this in Tango controls, but usually it is not really possible to make all those things work in a large system, because database could be dead and it will be restored, and meanwhile you still need the system to function even without a database. So the database is not the most critical part of the system. You need your hardware running even without a database.
Yes, but if you make an experiment and you can't save the data, then you probably kind of have to tell that, oh, shit, I'm sorry, it's recorded, but like we should like restart the experiment if for some reason the database was down.
Yes, but we are talking about different kinds of data. There is some kind fast data or data acquisition system, which is usually run in different separately from SCADA, from slow control, and things I'm talking about, and it is usually strictly peer-to-peer. So you have a detector, and you have a detector readout, data acquisition, and it's usually connected direct to detector. It's not distributed, and it runs completely separated from the SCADA system. The SCADA system controls your things like temperatures, pressures, some properties that you do not have a lot of data there. You have you read in like.
So it's not really a question of data. It's just that your data doesn't have like is somehow time independent, right? So you just measure this temperature, and for some reason, if you've stopped measuring it and then you restart measuring it, you don't care, right?
Yes.
But you might have a situation when you sort of want to kick off something and then measure the response, and then you kicked off and the database is down, then you sort of say, oh no, I'm not gonna record that data. So when the database is back again, then you want to kick off it again and to measure the response and then save it in the database. So
yeah, there are different things. As I said, in general, you can't be sure that every part of your system works fine. In general, it fails, and it's normal case. So most of the systems we are talking about, they actually have a localized data storage. So each device server has its own data storage. So the central database is used only for indexing and to centralize access. But data is usually duplicated on the servers which are used to acquire. So if some sensor dropped out of network, it usually keeps running in a standalone regime.
Yeah, but then if it has a database locally, then obviously from our point of view, it's just another service which is just co-located with that device.
Yes.
And then you're in the same sort of story. If the software fails,
it's not exactly like this in systems like Dux, where they have integrated storage and readout system. But in case, for example, for controls kit, yes, it's exactly the same. The local storage is additional service running locally.
Yeah, because they will so maybe running a bit ahead of time regarding your talk. They will be still communicating saying on ZMQ, right? Even if they're on the same machine.
No.
No, they're just gonna flush the data to.
We will keep this question until we are working with a specific device implementation. So what I'm saying, to answer the rest of the question, if something goes wrong and some device here just breaks, then there are so-called alarms. So if, for example, Watchdog can't access critical device, then it rises alarm, and there is a guy here, and it goes sad and says, please stop everything or it will explode. So, of course, the system can guarantee that all things are running at the same time, but you can at least be sure that it will raise alarm if something else goes wrong. And what I was going to talk about a little bit here is why synchronous communication. Here I wrote only synchronous response request. But the problem is that consider you are, I'm writing in a different color here. You are making request here, and he makes request here, and he makes request here. And this one to the left needs to wait all the responses back here until he can proceed, because he blocks until he gets the response. And if at the same time, someone else, like guy number 4 here, let's use different color. If at the same time, guy here makes a request, you need to, in most cases, you also need to wait, because if you have a synchronous system, then you usually can't change one of the properties while the state of the system is unresolved. This is the problem with the scalability. So the number of those connections is more or less, it's a rise with the number of nodes exponentially mostly. If you plan your system quite well, and then you're always sure that you will have one-to-one communication, it's okay, it's a linear. But in general, it could be a very complex system and very high response times. And the people in industry I've been talking about, they saying that it is always an issue, this delay for synchronous calls. So what we are talking about today, we are talking about scalable systems, asynchronous systems. And for that, you need to actually forget about request response. So basically, you want things like this. You have those. You can call them actors because they are actually actors. You have those actors, and you have some kind of event loop. And then something happens, you send event to the loop. And other people, they do not work directly. This guy number 2 doesn't work directly with this guy number 1. He subscribes to the loop and says, I want to get updates on what happens with number 1, all events produced by number 1. And so when the events passes, we're sent it here, and we know about changes here. And if we want to notify other people that something changes, then we say, again, we are sending this message.
So I think to me this sounds more like coroutines, because in actors, say node 1 will have its own message queue and it will just react when it gets a message. Whereas in coroutines, you have these channels, which you say, okay, I'm gonna pick up this channel and wait one, and so you sort of subscribe to something. Whereas in actors, they're sort of standing by themselves. They don't.
Yes, they actually both, because each of those devices here, they are working as actors because they both receive messages and can send it. It's not quite actors, because in actor you only have one input socket. You do not have output socket in actor, in general actor.
No, an actor can have reference to other actors.
Yes, but
can react.
It's not specified. It could be different for different types of actors. I will show you a Magix specification a little later. But the idea is that you communicate with messages, and you do not send message to, in general, you do not send message to specific actor. Instead, you send message about your state, not about their state. The positive side is that you have a scalability, because there are a lot of software right now which allows to scale those event loops infinitely. For example, Apache Kafka, which is quite broadly known, you can just easily add additional processing power to this loop, and you will get any scalability you want. And the downside is, as I said earlier, you do not have any assurances that the guy you are working with is alive, because there is no guarantee that event reaches its target.
So in Actos you have this broadcasting message box to which you can subscribe normally.
Yes,
but
exactly.
Kafka is more than that, because it has it's more like a message broker. So
yes, Kafka is not exactly a message broker; it's a message queue, and it has a lot of additional features. For example, it has a replay cache, so you have some kind of guarantees of getting your data to the destination, and it has a lot of duplication in it. Today, I'm not talking about Kafka. Right now we are talking about our own implementation of event loop, and we're talking about Kafka or similar things only in future when we need huge systems. Right now, we're not talking about it. I'm just saying that it is possible to use industrial software to scale those algorithms. And of course, another application comes from the fact that all nodes communicate in the same language. So they use the same specification for event, and it works more or less the same for everyone. Okay, I think, and I promised a watchdog, and if you, or of course, in this case, you also can have a watchdog or a database. Or the watchdog is just periodically sends events, for example, to all devices, and says, please give me some kind of message that you are alive, and then it collects all the messages from all devices with some kind of timeout, and says if somebody does not respond in a lot of time, then it's dead. And the same goes for database. It just subscribes for all the events going through the event loop, and that's all. Okay, I'm going to close this one, and I'm going to finally switch to the code. I'm not sure about the size, so I'll probably switch to the presentation also. It will be easier to show you the code. Okay, now we're going to this controls kit project. Oh, here it is. So a lot of things here will already implemented a lot of different models, but I will probably stop at 3 major points. First of all is Magix, and Magix is a specification we use to pass messages, and also the specification we use to connect new services. And for those of you that do not know, the model I've explained just a minute ago, it's basically a microservice model. So the Magix specification was developed by Igor Khakhrikov, and with my small help from myself, most of the documentation. And basically, this is the Magix server, so Magix endpoint. So the device which implements the Magix endpoint can subscribe to events from the loop, and it gets a flow, and it's Cortian's flow, or it could be RX flowable or whatever reactive stream library you use. And it could subscribe to the this lazy flow of events. And the second thing it could do, it could broadcast event. The Magix message is a simple thing. It's basically JSON message, and there is a specification here. It contains the information about where it comes from, where it's going to, the format, some additional security information, and of course the payload. And the payload is basically a JSON object which could have different nature for different systems. So this is the Magix endpoint, and we can probably just look at the implementations we have for Magix endpoint right now, and we have two basic implementations for Magix endpoint right now. One is the RSocket implementation. RSocket is the protocol for reactive streams. You can Google it up. It's pretty new in terms of software of this type. It's several years, and it's so new that it's pretty hard to build it on the C++. And the Kotlin implementation is also not so stable, but it's pretty nice, and it has a lot of high-level utilities to work with reactive streams. So
when you decode from string, can that fail then?
You mean that's a wrong format?
Yes, for example.
Yes, of course.
And so what happens in that case? The whole
this message is just ignored.
Oh, it's ignored.
Yeah, we are living in the asynchronous world, so we do not have any possibilities to respond to a message.
No, you don't have to respond, but if my point was that if you receive a message, or if you fail when you treat this message, then why don't you build into your API, into the Magix, whatever it's?
Yes, there is a
the whole loop for restarting the service to run again and keep on getting messages.
It's
or fail. It depends on the user.
It's not that simple, because if the service is dead, then there is no general way.
No, it's not dead. It's just you fail to process the message for whatever reason.
Yes, but there is an issue in the Magix specification, my own issue, about treating of errors, and it's more or less what you are talking about. So when we get some kind of error, we need to send a signal that you need to fix some things. But the problem is it is not possible to make the treatment of those errors general, because we are going to integrate different systems with the different vendors, with different formats, and they all have different treatment of errors. Yes, basically, when you communicate between two devices have a same specification, you want to get the response, get a error in response for your erroneous message. And as you will see later, it is, to some extent, it is implemented, but you can't guarantee those things on the level of standards because they're too different. Okay. It's a good question, but I fear that there is no good answer about error treatment. Of course, in general, you should send some kind of message that there is a error, but you also can't be sure that this message about error will be properly treated. Yes, so now in Kotlin, in order to do something in coroutines, we need to either pass a scope, coroutine scope, or we need to pass a coroutine context. It's more or less the same. The scope is an interface which has only one property, coroutine context. It is used to handle errors and dispatchers, I mean thread factory, logging to some extent, and other things that are passed with the coroutine context. Then you need to specialize your serializer. So you need, each endpoint can work only with the one type of message. It could be generic JSON, for example, if you want to be the most universal service, it will just work with a JSON object or JSON element. And you need a connection, which calls RSocket, which specifies where the socket is connected to. And those two are basically functions which work with a message. Here we have 3 lines. First of all, we create a in RSocket, it is possible to send initial handshake message, which is very convenient. It is not possible, for example, in ZMQ, but in RSocket it is possible, and we use this initial handshake message to pass the filter. So we do not want to subscribe to all the events. We want to subscribe only to specific kind of event, and we use it to minimize the network traffic. Then we just use basic RSocket method to create a flow. As I said, it's created to work with the active stream, so the API is super simple. And then we just create deserialized messages and pass them to our subscribers.
Sorry, so you seem to just in that case, to subscribe to a WebSocket stream, right?
It's not necessarily WebSocket, because RSocket works on top of TCP, WebSocket, and some other protocol. So we are.
But then I don't see any mechanism to handle if the flow is too frequent.
Yes, the flow itself. Yes, you mean the back pressure. The flow itself, the flow mechanism itself, since it's a suspending function, it automatically applies back pressure. When you start to read elements from flow, and you can't read them as fast as they can, the flow suspends, which means that no new messages are coming. And on the network level, the back pressure is handled internally by RSocket library. So
it's sorry. So it's the RSocket library, or it's the coroutines implementation of
both. I mean, if you just use it locally without the network, then in coroutines, I mean in flow, you do not need to apply back pressure, because it's automatically applied as soon as you stop reading from flow. It suspends and it suspends all the chain that leads to this event. So it will automatically suspend on the other side as well.
Okay, and is it easier to configure the buffer?
Much easier, and also you can actually do buffers and in the coroutines as well. You just use a buffer, and here is the flag on buffer overflow to treat different kind of back pressure strategy. But basically, when you're working with a coroutines flow, you do not need to think about the back pressure. It is handled automatically by the machinery. Of course, it's not the same when you want some kind of back pressure to apply it via network to send actual signal that you need to stop sending me new events.
That's not scalable. I mean, this is too much luxury.
Yes, but I believe that RSocket have some kind of mechanism for that as well. As I said, it's very nice library in terms of usability. It handles all those things about reactive streams internally. And as you said, there is a problem, and I agree that this is a problem. And in here we can have a error. It will. I'm not actually sure what it will do if it encounters wrong message. I believe it will just propagate error downstream. So when you try to read from this flow on this particular message, you will get an error on read. But it's a good question, and we definitely will.
Yes, yes, exactly. So how do you? So in reactive streams, normally you propagate the exception.
Yes, it's exactly
the same.
Yes, exactly the same. So you will get an exception when you try to read this element. And you can add.
It's up to so different subscribers can handle that exception differently.
Yes, right? Yes. And you can, of course, you can write this thing and catch the exception here and not propagate it further. But I'm not sure it's a good solution at this stage.
And sorry, so just a question which is of interest is that so for those Magix, sorry, it's called Magix services, right?
Endpoint.
Magix endpoint. Yeah. So Magix endpoint. So if you want to have a pattern when you sort of launch those Magic endpoints in a specified sequential way, so you don't launch one before the others. How did you have to implement some sort of manager and slave, master and slave architecture?
Yes. So the idea is that we are using the most simple building blocks, and then create a complicated system from this building blocks. We try to do not make this architecture frigid. And in case of endpoints, they usually eternal. So then you usually start this endpoint on this when the device starts, and then you do not kill it until the whole operation is finished. So usually you need to restart it only if something fails. And the second thing here is a broadcast message. It's just.
I'm so sorry. I just. My little last comment is, I guess because you do have a sort of protocol, right, for your JSON. So every single new system you want to sort of to be part of your controls KT architecture, you would have to encode somehow the way the messages will be passed. So it's in that sense, I was imagining that you could force the user who wants to integrate, say, some new crazy device with some new crazy software stack into your system to actually think about how it's going to behave itself when it fails.
Yes,
it's in that sense that I was expecting you to kind of make it part of the API and not.
Yes. By the way, what we really should probably do here, it's Russian. We need to check format, because that thing we can do. We can check incoming message and ensure that the format is the same we expect. Format field, I mean. As for different types, yes, I agree with about the errors, and it was one of my first questions actually when I saw
because in the way you formulate the API, to me that means that you sort of expect the thing to run forever without any problems.
No, of course not. Of course not.
But yeah, but then you need to kind of force people to actually. Yeah.
But starting up and closing down servers is not handled by this API. It's handled by its own manager. I do not think it's possible to do it otherwise. Because you just can't start the servers on a remote computer in general.
Yeah, but it has to decide itself how it restarts.
Yes, of course. And each system has its own way of handling this thing. As I said, in this case, we are switching to this context, and I'm not sure because why did not we use this? We should probably also use this flow on origin context. So we need to ensure that all messages are evaluated inside this context, not on the context of whatever we used to get them, not on the RSocket.
But are you sure it's not sort of automatically part of the?
No, it's not, because here I'm using a request stream. It means that if I'm using not a lazy stream but hot stream, not cold but cold, it will use a thread pool from RSocket and all its context, and we want to evaluate messages. We do not want to pollute this pool. We want to use our own context to evaluate messages. Yeah, okay. Here it is pretty simple because we are just firing an event and we just do not need to think about how the back pressure. And the back pressure is actually automatically applied because you can see symbol here, and it is a suspend function. This fire and forget, it's a suspend function. So if everything is stopped on other side, I mean, if the back pressure is applied, then we will have automatic back pressure application here. We do not need to think about it. Now, probably for you, it's most important thing is the ZMQ endpoint. And I need to be clear that I am not an expert on ZMQ. So I'm not sure that my implementation is very good. So it's a very basic thing. And because ZMQ have its own problems with it has its own thread loop, and it's a pretty low level, so it's not always clear how to work with it. Okay, here we have a host, and we have two different ports. In case of RSocket, it's a bidirectional, but in case of ZMQ, it's unidirectional. So we need one port to attach pub-sub socket and one port to attach pull-push socket. I'm not sure I'm correct, but I did not find other way to do it. And we also need a courting context to hold everything. In ZMQ, we need to create a context which holds all the references, and it's used for garbage control and the lifecycle control of this thing. And here is the code for subscription, and it's much more complicated, of course. We need to create a ZMQ socket, and then we need to connect to things. Then we need to, I'm not sure why we need this, but it won't work without it. So we need to add additional property subscribe, and if we go inside, we will see that it just sets the specific option of the ZMQ socket. And I'm not sure why it won't work without it, but it won't. And then they create this channel flow. Channel flow is a hot flow. It means that it's basically, we usually assume that flow is cold, which it produces new events as soon as old events are consumed. But a hot flow, like channel flow, is constantly producing events and suspense only when the channel is saturated. And we are using
so why won't you use channels here?
We do not use channel explicitly. We use a specific kind of flow which called channel flow.
No, I mean, instead of having a var for which you keep on testing the so you write a while loop.
Yes, it's exactly the same, but we need to return a flow. So we need to here it is your while you are talking about. But I need to return a flow, so I need to convert the stream of events in. I need to convert the callbacks I get into the flow, into the reactive flow. So
this should normally sit on. Yeah, I'm just. This code, line 43, looks like C++ to me, whereas we are in the
yes, exactly. And I did not find any other way because, sadly, if ZMQ would allow us to use callbacks or receiving a message, it will be much more compact and much better. But sadly, ZMQ API does not have callbacks. So in order to read something from ZMQ, you need to constantly make requests like this. And you need to do it in a loop. I did not find any other way. If you know any other way in C++, please let me know, because our people who were working with ZMQ on C++ side, they have the same solution, exactly the same solution. There is no other way, sadly. You just have to call it in the cycle and API. There is another solution which allows us to call it with a flag which says don't wait. I mean, don't wait to receive new string, but return immediately and return null if it is empty. But in either case, you will need to have some kind of timeout. I will show you later. There is on the server side, we use a timeout version of this one. here I use it in order to properly close the connection when everything fails. Okay, and another thing which is not so good about ZMQ, that I don't have this handshake package. I can do it, but it will be a very complicated logic. So I do not have this handshake package, and I can subscribe to specific type of event. So I'm doing this filter. You remember in RSocket, I passed this filter in the handshake. In this case, I just filtered on the client side. So I receive all messages, but then filter only those that I need. The publishing is much, much easier, of course. Of course, I need to create a publish socket and hold it until the endpoint is closed. Otherwise, I will have a lot of creating new sockets, which is not good. But after I create this socket, it's quite easy because I just make send, and it's fine. It works. And of course, I need to ensure that the ZMQ context is closed when it's closed. So this is for endpoints, but it's not the only thing we have right here, and we are talking like 50 minutes, so I probably won't go into actual controls kit today. So I need to show you the server because it's also important. And here it is. Let us see how it works. Currently, the server, it implements all different approaches to all different protocols. So when you use it, there's a function which starts in Magix service, and it starts a Ktor server, which implements 3 different protocols. Oh, four. First of all, it implements a RSocket. Sorry, I know how it sounds. I mean, it's a TCP/IP based RSocket, and it's uses default port for that, and it implements the raw RSocket. Let's see how this looks like. And basically, in order to do that, we need just to create this access acceptor, create the instance of this acceptor, which is pretty nice, and it handles different kind of requests. It's a request stream, fire and forget, and request channel, and it also uses bidirect communication. We do not use bidirect communication in our endpoint, but it is also possible in Magix, in the RSocket, which is very nice. The second thing is the ZMQ server, and we can see how it looks like inside. Again, it's not so clean, but it's much clearer than C++. And you see that we create this context, and inside this context, use ensures that the context is closed when we finish using it. It's like a try with the resources in Java. And we create a publishing socket, and then we, here is a very important thing that which I missed. Oops, there is some kind of questions, I do not see it.
I'm sorry, yeah, just, maybe I'm a bit wrong, sorry, Alex. But I send you a link to the Scala reactive ZMQ implementation. They're actually using a sort of tail recursive.
It's exactly the same. I looked through the Scala implementation, and it's exactly the same under the hood.
But it's sort of...
The tail recursion and the cycle is exactly the same. You probably know about it. So it's a tail recursion is a different way to write the cycle.
Okay.
Because it's just that Scala people like those functional approaches, and they tend, in some places, they tend to use tail recursion instead of cycle, just because they like it. But structurally, it's exactly the same. okay, what is very important thing here is that this guy, because in the server we need to create event loop, and here I've created an event loop in one line of code. It's called immutable shared flow, and it's pretty new thing in Kotlin. It's like less than a year ago it was introduced, and it's very nice thing, and it's actually an event loop, so you can write things into the mutable shared flow and get the shared flow which is not mutable out of the other end, and you can subscribe on it, and you can even have a buffer capacity for this mutable shared flow. So new subscribers will have not only the events that pass after they subscribe, but limited number of items which were sent before they subscribed. And here we use this mutable shared flow as both input end and output end. So we are continuously pushing events inside and reading events from the other side. And we are pushing new events when we have some push from the endpoint and continuously reading elements and serving them to all endpoints.
I'm very sorry, Alex. Sorry. I just yeah, it's just nice to discuss, but just there is a difference though between the way Scala has formulated that. Is because they've put an actor which has its own messaging queue, and basically what you do with this sort of while or tail recursion is that you send messages to that messaging queue, and the actor processes them. And you can actually send a message to the actor to say stop receiving messages, and it will just stop receiving that. Whereas in your case, you have a while loop, you can't. You can't interact with this while loop.
It's exactly the same. Let me get back.
If you were using channels, then yes, it would have been the same thing. But you're not
exactly
using
the same.
How do you kill
inside,
this loop, for
inside
example?
we have a producer scope, which is actually a channel. Yes, it looks more.
But how do you kill this while loop then?
Just set this active flag to false. That's all.
Yeah, but then this is you kill it through mutable state.
Oh, it doesn't matter.
Because normally I would expect an actor who just gets those messages, and if it encounters a stop message,
it's exactly
then
the same. I'm just implementing this actor.
The problem with this approach is that you have a mutable state, and you could sort of say, stop this while flag, and then it will just.
It's not visible from outside. It's this flag is visible only from inside this channel flow.
But then how do you kill this while loop?
If you can see that if I cancel the flow, then automatically I will get the cancellation exception from this.
If you cancel the...
Yes, it's a structured concurrency for you. When you cancel the scope in which the coroutine is launched, it automatically cancels all coroutines inside it.
And so what happens if you are in the middle of...
It will throw a error here.
Everything, so...
It will throw error here.
But why will it...
You can't
just drop the connection, freeze the resources, and then...
Yes, because let's see here. If we close the ZMQ context externally, it will automatically throw error here, because it's how the ZMQ works. When the context is closed, it throws errors inside.
Yeah, but I would have preferred the guy to sort of receive a notification that I want to cancel the flow, and then just unsubscribe gracefully from the ZMQ and then carry on with the flow, instead of throwing in the middle of a socket connection.
Yes, okay. You don't have any way to interrupt this thing because it's a blocking operation. No way in Scala or Kotlin or whatever you can.
Yeah, but
so in this case, if we have a cancel, then here I will have a cancellation exception, which is not normal kind of exception. It's treated by coroutines mechanics differently, and it's exactly what you are saying. It's a soft cancellation. And I will gracefully close the connection at this point. If I want to additionally check that not only in this point, but if I want to preemptively cancel the sending before this, I can do this thing, and it will mean that it will throw the same cancellation exception here before I start, before I try to read. But I'm not sure it makes a lot of sense.
Yeah, but
we can do that.
JRMQ should have a disconnect method.
It
has a disconnect.
Here it is. Maybe we can. Maybe we can do it.
So when I tell you cancel the flow, you have to call the if you want to do everything gracefully, then you have to call the disconnect, the JRMQ disconnect method.
Yeah, I can add it. I can add this. I can, for example, say something like.
Yeah, but coroutines have channels.
Yes, I'm working inside the channel right now. If you see how the channel flows works, it actually a lot of code here. I'm not sure I will have time to. But it's
because normally you have this channel and then you sort of.
Yes, this is exactly what.
To this channel.
Yes, it's exactly because the channel is hidden inside the channel flow. What I'm using here is producer scope is exactly the channel.
I'm sorry, I'm just so annoyed to see a while loop in Kotlin.
Sometimes you can't avoid it, and if you want if you want graceful close, then you can do like socket
disconnect. Yes, you have to call this somewhere. And this normally should happen in a finally.
Yeah, we can do that. But yes, we can do that. Yeah, we can do it. We can. I use socket close, which is exactly the same, and it will probably disconnect. So
not. Yeah, but
this is actually it can be called to ensure correspondence has been disposed of. So I think that
normally you should have been freeing all the resources and closing everything.
Yes, I hope that it does exactly that. I'm not sure, but I hope that it
verbal while try catch in Kotlin is.
No, it's okay. It's okay. And again, I'm saying that if ZRMQ would have a non-blocking way to do this, I mean, with some kind of callback, it will be much cleaner. But generally, you can't avoid this thing. In Scala, it works exactly the same. They call the same method here. They use it with a timeout, but actually they're doing the same loop, even if it is done with a tail rec, which is exactly the same as I said. And they are just wrapping it in different primitive. They're using actor while I'm using a flow, which is not the same because the flow is a infinite output and actor is an infinite input, but the idea is the same. Okay, we've spent a lot of time, so I have very little time to show how this works with this central loop. And again, I'm will be very happy if you have some insight about other ways to do it in ZRMQ because I am not familiar with.
By the way, I don't C++ guys are not there, but normally you also do it you have actors in C++, and normally you manage such connections with actors as well.
Yeah, as I said,
in this case, asynchronous and fault tolerant way.
As I said, the Kotlin scope does it for you. Because it's also allows proper error propagation and cancellation. This is the idea. Actor works as a scope, but in Kotlin Kotlins, the scope is much more universal, so you can do it without actor. The thing here is that we have the same event loop flow for all connections, meaning RSocket, ZMQ, and even two connectors here, which are here we have also two connections inside a Cater server. One is for RSocket with the web sockets, we probably need, yeah, here it is. It's an RSocket with a WebSocket and uses the same acceptor. And the second one is the simple HTTP plus SSE connection facility as well. We do not use it right now, but it is also a possibility. Okay, I hope I explained things to you. Very short, deep into the actual device API. I probably won't do a lot of talk about it today, but let us go to the demo and see how it works. And I've changed a lot of things recently, and let me show how simple device works. So this is the whole code for a device. And here a device has a specification which defines properties. Here we have 3 different writable properties. All of the type, all of the type double, and we have is called scene scale, cost scale, time scale. Also, I have a computed read-only property, which computes on call. So use a current time and corrects for values of current time scale and scene scale. Here we have a little bit of magic here, because you can see those properties are defined in companion object, and companion object is in Java it would be static. I mean, it's a single instance thing and not in actual device. But we have here a property of a receiver. I mean, when you compute, you substitute the actual device on actual device state here. And we have some additional things like actions and additional code which will be executed on the device startup. And in this case, we will read, force read values from scene property and cost property on each 50 milliseconds. And all this left is to define the state of this specific device, and it's quite easy to do. I think I've got a pretty nice API when we have all the description of those properties and actions in the immutable specification, which is the same for all devices, and you can have very smallish compact state for actual device. And probably I can launch some kind of demonstration if I remember which one to use. Yeah. I've moved the project to the new computer, so we'll need to wait for a bit for it to compile. Okay, we're a little bit out of time, so probably the next time I will talk about the device API in more detail. But today there was a request for the streams and event loops, and I hope I explained things. And again, I'm not sure about how it should work with the ZMQ. For example, right now we are using 2 sockets to publish and to subscribe. And if we want then to do some kind of message brokering, we will do it via our own event loop, and it will be much slower than using ZMQ internal facilities. So maybe it will change. Oh, some kind of.
Sorry, what do you mean by? If you use a message broker within ZMQ instead of what?
I mean, right now we are kept some years here. So it's a wrong Kotlin version for some reason. I mean, when right now we are capturing all events in the ZMQ and translating it to our event loop and then working with them. If we want to use a ZMQ loop, then we catch the event, then send it into our event loop, and then broadcast it again to subscribers. But it's not efficient because ZMQ was designed to do those things internally. So
exactly. Why you don't use?
Right now, I use it because I wanted to share the event loop with the other protocols, and there is no other way. Maybe there is other way.
You could flush everything, just flush everything to ZMQ, and then.
Okay, as I said, it's not set in stone, and I'm not sure about those kind of things, and I'm not sure even that the ZMQ will be the primary protocol for us. Right now, I like RSocket much better, but it all depends on.
Yeah, but RSocket is not a message broker.
We can use it with a message broker. We can send our RSocket stream into the.
Yeah, but then this is extra stuff. This is extra.
Yes, right now, I think that for the scales we are using right now, the homemade message loop based on coroutines is all that we need. It covers all our needs. But in future, when we will scale these things, of course, we will need to think more about how to implement the inner rule. On the plus
by
side,
the way, actually compared Akka to Kotlin's coroutines, you can serial. So they're location transparent. There's location transparency in actors, in the sense that you could use this Akka remote thing where actors are running on different machines and talking.
Yes, I know about that.
But coroutines don't come build with.
Yeah, for some reason it catches the wrong version.
It's a specifically local multi-threading.
Yes, I know. It is possible. It is also possible to do a lot of things in coroutines, and I know that Akka have special facilities. Okay, I will close it right now. I will show you the demo next time because there are.
Yeah, don't worry about it.
So some kind of errors. For some reason it catches the wrong version of Kotlin.
Yes. Yeah, because you have to update. There is a Kotlin update, right?
No. It's a Kotlin datetime library. It's right now. The version is for some reason incompatible with the current Kotlin. I know this exception. I'm not sure why. Actually, I think I know why it is. It's because of RSocket. Yeah, I know. Okay, don't have time for that now. It's fixed, but not in this demo. It's fixed in the other demo with the ZMQ actually. So yes, there are a lot of ways, and what is important right now for us, I mean from myself and for Igor, is that we won't have to change the protocols, the connection endpoints, etc. if we want to replace inner logics. For example, if we want to switch completely to ZMQ brokering, we don't need to change anything. We just change the implementation inside this ZMQ endpoint. If we want to use more complex thread pooling inside this event loop, again, we do not need to change everything because all the connections are specific and they do not depend on how do we implement this event loop. This is actually the problem of systems like Tango and Dux. They're reliable on the broker system, and you can't use them without. For example, Tango is reliable on Corba. Roland, you are probably old enough to remember Corba. No, you don't remember Corba. Corba was a huge project, huge industrial standard, like 15 years ago or 10 years ago, and this idea was that we bring everything together, and the serialization and the message brokering and balance loading and device and endpoint discovery all in the one huge industrial standard. Yeah, this was the idea that you just plug it. Oh, it's my daughter. You plug it and it works. But the problem is it doesn't work. So now the technology is outdated, and we have to use a technology which is not supported anymore. And we can't replace it because the serialization and the discovery is tied to this technology. This is why we want to do is as simple and as modular as possible. The same goes to Dukes. The same goes to Dukes, which uses Sun ONC, which is even older. It's much more simple than Corba. This is why it is easier to work with. It's not a complete huge system. It's only serialization and remote procedure call system, but it's also outdated, and they used some bizarre modifications on top of it. So you can't use them outside the system. You have to use the C++ implementation they use, because otherwise it is not possible to implement these things. And in this scenario, as I said, the implementation could be different. For example, for this event loop, I have 2 different implementations, and Igor Fakrikov has additional implementation on top of Tomcat server. And we can add new different, but we don't have to change protocols, and we don't have to change rules.
Can you advise me, do we have like a nice reactive stream connector to Redis in Kotlin?
I believe yes. I never worked with this, but I heard people talking about it a lot, and I believe everything is there. Yes.
Okay.
Okay, I think we should finish for today. Maybe any other.
Thank you, Alex, a lot for a nice talk. Yeah, nice comments.
We will have additional talks like this. Are there any other questions? Okay. No questions. Then I'm stopping the recording.